All right. Hello, everyone. Happy Monday. Hope everybody enjoyed Super Bowl. Everything was good except how it ended. But oh well. That was my first full Super Bowl. I enjoyed the halftime show. It was very good. All right. So Brett will be late today. So hold your questions for Discord, or you can either ask me or just wait for him until he shows up. All right. So this week, today and Monday, I'm recording. I'm not muted. Okay. Today and Monday, we're going to talk about basic form of first order and second order system. Just give you some specification. Friday will be practice exam. So I'll bring some problems. I'll post them before. So if you wanted to take a look at them and then know what kind of question we'll be working on Friday, feel free to do that. And Friday, we just do those. The exam that I submitted, I said the date wrong. I'm making so many mistakes. It is a practice exam. You don't have to do it. It's just for you to kind of get to know the conceptual question, but I still made it a quiz. I gave you the passcode. So you received a passcode from me. So for those of you that are here, I think you can take the exam. I would suggest keep the exam until you want to study. You have 3 chances to do it. There's no time limit, and it's open until Monday before exam time. So I suggest study first, do the problems, then do conceptual. So leave that for the last thing you do. Just make sure that you got the concepts down. All right, that would be my suggestion. And again, does not count toward your final grade. And you probably won't see any grading because I say that's practice exam. All right. So today you will start with first order system, and then I'll introduce second order, and then on Wednesday we'll talk about second order more. So basically, we have some standard systems, a standard form of system, and we have some standard form of input. If we can put our system to those standards, or if we can realize, hey, I have a second order system, or I have a fourth order, but I can divide it into 2 second order system, it's in our benefit to do that, because then we know how the system would respond. So we have an idea of how the system will behave. So we want to make sure that we are familiar with first and second order system. You have seen them a lot before. In this class so far, this is week 6. Some of our example was either first order or second order, and in your previous course, especially anything circuit related, you have seen first or second order system. All right. So we are basically classifying the response of some of these systems that are around us. Now, for system, we will only focus on first and second order. For input, we will focus on impulse, which we already saw before when we defined the transfer function. It's just a very high amount of any force or any input for a fraction of a second for a fixed amount of time. And then after that, there's no force. So just like impulse shopping, you have a big urge of doing something, and then before that, there's nothing. That's impulse. Step, the example of a step you saw in our Friday class, right, in the coding part. So U of, let's say, T, or input will look like 1 of T, or so if this was 1, it would be unit step. If it was 10, it would be step of 10, which was your class participation. So this, whenever you have input as such, it's a unit step. It means that your input looks like this. For any time before 0, we don't care, it's 0, and then at that time it's 1, and it remains the same amount. So that's the step input. The next input we are very interested in is ramp. So ramp is U of T, your input is T. As time goes, the input increases the same amount. So basically, it would be a straight line. So this would be Y of T, the output. This would be your ramp, which is T, and this is 1, right? So these are a standard input. we know how the system behaves when we apply a standards input to them. So we are going to study them for first order and second order. And once we have those down, if our actual system is a second order system or two first order system, then we kind of have an idea of how it would behave. Why do we need to know? Why do we need to expect or guess how does our system behave? What is it good for? What is it that we want to do in this course specifically? Control, right? You want to control the outcome. So if you have an idea how the system behaves, it's easier to control it because you know what kind of controller you apply. Because there are so many different methods. But if I know my system is second order, and you're going to see there's only four behavior that the system can have, depending on which one you want, you can look at the current response and say, hey, I don't like this. I want it to be like number 2. And then you can apply your control to look like that. So that's the reason we want to know what system we have. Is it first order, second order? We want to know what input we are applying because we want to control the output. So once we know, because in control problem, we know what the output should look like, right? So we can pick the input. And we know for LTI system, we can add multiple inputs, right? And then get a new signal. And if each of them separately applying the system have a desirable output, we can add all of them and we'll have the desired output at the end because the system is LTI. So based on the definition. So sinusoidal is just a sinusoidal wave. For now, we are going to, there are different kind of input like sawtooth. There are so many other ones. For our application, step and ramp usually are the two that we are focusing on. So any problem you get, pay attention to the order of your system and what kind of input being applied to it. All right. First order system, you probably have seen this before. Any system that's in this form, some tau could be 1, right? Some coefficient times y dot of t, first derivative, plus y of t now is equal to k u of t. So u of t is your input. It could be anything. It could be 0. You could not have an input or you could have an input. Now this u of t is that step or ramp that we discussed. So if your input is a step, instead of u of t, we will put, for example, 1 of t. So k is just a coefficient. You can amplify that. So if it is unit step times time, times 10, then it's input of 10, right? Now, we like to put them in basic form. And then once we have the basic form, we can predict things about them. So if you have a first order system, your basic form should look like this. The transfer function will look like ys over u of s, which is your output over input, k, this k, over tau s plus 1. So s here is S domain, right, is the object of transfer function. Here, having 1 is really important. When you have 1, this must be 1 to be in basic form. So if your transfer function looks like this, your system is first order. So if you had the time domain specification, it should look like this. If you had transfer function, it should look like this. If it is a first order system. Now, if it is a first order system, the key parameters are your time domain, which is your time constant, sorry, the time constant tau, and k, which is your DC gain. Now, if it was time domain, you can realize from the input, right? If it was your transfer function, there's a little bit work to do, but if you had in basic form would be the numerator, whatever that k is. All right. So what if it wasn't in the basic form? What does it mean? What if your transfer function g of s was, let me say f, so you know this is an example, was some c over tau s plus a. Is this in basic form? No, because we look at this here, has to be 1, it's not 1, we have to put it in the basic form. What should I do? David? Divide by A, yes. So my new transfer function, right, I'm gonna call it, I'm just gonna say G prime, but so it's C divided by A, how divided by A S plus A divided by A, which is 1, right? So I'm gonna write this 1. Now we have it in basic form. Now, if you compare, you see that your DC gain changed, your time constant changed as well, right? That's why it's so important to put it in basic form when you are in S domain or transfer function domain, all right? Now I know my time constant is tau over A now, and DC gain or gain is C over A. So if it was a mechanical system, its gain was electrical, you can say DC gain. Yes. So if your system is first order, your transfer function always would look like some number on the numerator divided by S with some coefficient plus some number. Now, if that number was 1, it is in basic form. So if you had it in basic form, like look at here. If let's say your H of S was 100 over 5S plus 1. This is basic form, right? If I ask you what's the DC gain, what will you say? 100. You just look at it, right? You see this is basic form, so the numerator must be my DC gain. And then what's time constant? 5 seconds. Time constant is seconds, right? 5 seconds. You got it. Can you recognize what system in electronics this transfer function belongs to? Who's in technical writing this semester with me? What filter did you get? Okay, it could be high pass or low pass. Yeah. If it is a RC circuit, that's a high pass or low pass. If it's LRLC, it's not. So this could be a low pass filter or high pass filter. So a lot of systems around us have this governing equation, have this basic form. So if you can convert it to basic form, you can easily say what's the time constant of my filter, what's the DC gain, the gain of my, which is one of the requirements in design, because you need to know once you found the frequency that you're filtering, what's the actual gain that you're receiving, right? So that makes sense? All right. What else did I have? Okay, I already talked about the, let's say here you have resistor, capacitor. Let's say you're measuring voltage here. This is your, well, let's say this is VT because we're interested in this one. This is some V8, V1, P. Right? So if you had something like this, well, you can read the voltage across resistor or capacitor, right? So this is an RC circuit. The filter could be high pass, low pass, depending on where you're reading the voltage, right? It will have the same basic form, which is one, well, K or gain over tau S plus 1. Now, I'm deviating a little bit from control to circuit because we're talking about filters. If it is a DC circuit, like it has connected to a battery, what's your gain, maximum gain? You should have seen it in the 2020 lab. What? 1 to 1, yes. So if you have battery connected DC, so for that specific filter would be 1, but you could have more gain, and that is if you had AC connected. If you had some gain in your input, then you can have more than 1 in your filter, right? So these are, so I will try to bring back information from your previous courses to control for you to understand control is not just about mechanical. electrical engineer should be able to design a controller as well as a software or a mechanical engineer. All right, so so you could write a transfer function for this, or a first order or a differential equation. If you write a differential equation, how would it look like? Like what form do you expect to see? So maybe RC, which is, if you remember, that's your time constant, some E dot T plus some VT equal to your input V1. Its first order is in that form, so you can't tell. If it looked like this, you know what's the time constant and what's the DC gain, right? Here's one. Because this is a direct, like a battery, but if it was AC, then you had something times sine of something, and you can find the DC from there, right? The gain from there is not DC anymore. So let's say you have this. So now you understand your system is first order. You can tell from transfer function. You can tell from this equation. Do you remember the response, the time response of the system? Let's say of this filter. You use it in 2020 or your other courses. Do you remember? Do you have like this is just a trivia question. Do you know how would you expect the output to look like, or the response to look like? Great. Oh. So from the fact that I said this is a low pass, you kind of know that it just kind of ramps up and then flats down, or if it's the other way around, like if it's the low pass or high pass. So you kind of know what kind of responses you're going to get. So I'm going to show you mathematically once. I don't expect, I will not question you in the exam on doing it, but I want everybody to understand how we got that, because we're just going to use the response from now on. Okay, so I'll do it once, hopefully you can follow, and then we just use the solution. All right, so let's say we need to know what kind of input we have, because it depends. I'm going to use a unit step. So unit step, here is unit step. UT is 1T. And I know my first order has a basic form. So I have the transfer function, right? If we get Laplace, since that one is in S domain, I need to convert my input to S domain. If we get the Laplace, U of S becomes 1 over S. How? Just look at the lookup table. We want to find Y of T, the response. So basically, we're trying to find what is Y of T, what's the response, the step response for this to this system. So from the transfer function, I know Y of S is GS times U of S, right? So input becomes important here, because right away it will be multiplied by your transfer function, by the system. So I know K over tau S plus 1 times 1 over S is going to be my Y of S. So to solve this, or to get Y of T, do you remember the process? We would use partial fraction expansion, right? TDS, but I'm going to do it here. So partial fraction would say that I'm going to say A over S, I don't know what A is, right? Times B over plus B over the denominator over there. So we're going to match the right side and left side, find A and B, then we have the whole transfer function. So to do that, I'm going to, well, let me write partial fraction expansion. You probably will find it in the book. If not, it's fine. As long as you understand this one example, I'm good. So here, A times tau S plus 1. So I'm getting the common denominator. And then that one is plus B of S, B times S. I'm gonna factor out S. So my S and my 5s look the same. I tried hard, it ended up being the same. So if anytime you have a question, ask me. So factor S, A tau plus B, right, plus A. Then S, tau S plus 1. Now, if you remember, we would use matching numerator, S to the power of 1 and S power of 0. From one side, so here we have K times 1 is K, right? So K doesn't have any S to the power of 1. So from that side is 0. From here is A tau plus B. So this would give us A tau is negative B. And from the rest, from the other side, you have A, so S to the power of 0, which is our constant. K is equal A, so we know what A is. So I can say K tau is negative B. So B is negative K tau. So why these two are important? Because then I can get the whole Laplace of Y of S and then Laplace inverse and find my Y of T. So Laplace inverse of Y of S. Who has bad dreams when they see this? Me, I remember that I did. But good thing, Dr. Z is the only one doing it. You're just watching. So inverse, so K over S, because we find that out, we find A and B plus B is negative K tau over, so I'm here. So I'm trying to fill out this equation here. Like I'm here. Tau S plus 1. If you get the Laplace inverse, meaning go to the lookup table and find all of those, you'll find K minus K e to the power of negative T over tau. We can factor this out. This is the part that you need to know. You need to remember. There. No, I was right. I think my annotated might have a little bit of problem. For T greater than 0. All right, so this is your Y of T. That's the thing you need to remember. So Y of T for first order system is going to be K times 1 minus e to the power of negative T over tau. Tau is your time constant, K is your DC gain. All right, now I have it again here, so I'm just going to the next slide to show you. This is what you expected, right? It's like a filter, right? So we know how the response should look like. Now, for different systems, K and tau are different. So the only thing is this becomes taller, shorter, wider. That's the only difference. You need to find those specifications from transfer function. Then you apply and you can draw this. So if I give you a transfer function, you should be able to draw this by hand without using MATLAB. If I give you the response, you should be able to write the transfer function from it. So I'm going to show you the process of how would you plot this by hand. So that would be your process of, if I give you the plot, you could write the transfer function. Make sense? Everyone's awake? This is important. Might show up in your exam. Yes. In homework. Yes. So you want to pay attention. All right. Yeah. So wake up on this part. Let's say to plot things, there are a couple of points that are important, right? One being what point? 0, right? So let's say at time equal to 0, Y of 0 should be K times 1 minus E negative 0 over tau, which is going to be 0. There, we have the first point. Then, since we know how the picture, the plot looks like, what is the other very obvious point that we can try to get? Tau, our time constant, right? So let's see if time t was tau, Y of tau would have been, I'm just following the equation, K 1 negative E negative tau over tau. 32 times K. So this is not K like 10 to the power of 3. This is K as DC gain, right? So where K is DC gain. All right. What is the other point? So if you look at the graph, tau is this point, which is 0.632K. So we have these 2 points so far. What are the other points? What point? 4 times tau. We will discuss why that's important. What's the other point that you think you could try? Infinity, right? Because it looks like it's kind of flattening it out, right? We get back to 4 tau, but I want to just talk about the obvious point first. So when I say time equal to infinity, have we used some other definition for the response of a function at time infinity? See who remembers. This is the part when I point at someone and then you all get mad at me. Don't call my name. There are a couple of reasons I do that. 1, come ready to the classroom. 2, I see someone is falling asleep or not paying attention, zone out, or try to bring their attention back. Jesse. Final value, initial value. So you found initial value, time equal to 0. You're finding final value. Great, good job. So FVT, you always, you can't find the final value of your first order because that one has all the poles on the left-hand side because of the 4, right? So I can say tau equal to infinity. Y of infinity is K, 1 minus negative infinity over tau, right? This is going to be K, very important. Your FVT, your final value is your DC gain. Makes sense so far, right? Now, what is the other point I have there? Tau is 4 tau. You will see this later. So that's one of the points that you want to make sure you check, and it's important for our controller. What happens 4 times our DC gain? So y for tau K negative 4 tau over tau. So tau is basically not important here. This is always going to be 98.98 K. At this point. Well, I'm going to do this so you know. This is the point that if that point is close enough, within 2% of, so it's between 2% of your DC gain, right? If that point is close enough to what you want, you can let it go. You don't have to tune the controller after that. You're happy enough. That's our happy enough point. Check 4 times the time constant. If it is within the 2%, is close to what you wanted. Let's say we were trying to track 1. If it was 0.98, you say, okay, I'm happy. That's good enough. All right. So that point becomes important. So you have 4 points to check. So if I give you this graph, you go find those points and then do backward. So one is, if I give you the graph, your DC gain is very obvious. You can read it, right? Just draw a line from the infinity. And then your 0 is always at 0. This point, tau, this is always 0.632K. So if you had your K, you can't find that value. And it's your Y of tau, right? So it's like reverse engineering the whole thing. Now, who remembers the significance of 0.632K? And someone is saying it. Louder. Right, 0.7, negative 3 dB. Yeah, I'm awesome, I know. Just giving free stuff. All right, so that's where that negative 3 dB comes from. All right, so everything has a reason in engineering. So we just don't memorize things. Hopefully this course will put other courses in line for you, like how they are related. All right, so this is first order system, the response, right, to step input, because we are trying, why this is a step input? Because I'm trying to get to, so our input actually, this is your input, and then your output is trying to track and get to one. That's controller, they're controlling. Now, would we like to be here or here? The dashed line or the solid blue line? The dashed solid line. You want to reach to your value, desired value, the fat sooner, right? So that's obviously desirable. Now, how soon you want to get there? That is your $1 million question, because sometimes too soon is too expensive. And sometimes too soon doesn't matter, right? So if I'm trying to go from 0 to 25 in my car, if I'm driving a Jeep, I can't get like 0 to 60 in 4 seconds. My husband, on the other hand, has a V8, he can. So the system will limit you. So you don't over design your controller, because the system can't handle. I just rev, don't go anywhere, right? So the understanding of how fast my controller should be, it's a design decision, it's your job. You have to just look at your system, the conditions, what you want, how much your project is paying, and design your controller. But you know that your desired response is one of these lines. Make sense? That is if your system was first order. Now we have all of this for the second order system. All right, so what I'm gonna do here is, I'll do this example, then you take your class participation, all right? So let's do this example. Hopefully it will fall things in place for you. The question says, determine the transfer function of a system that produced the following output. So the question is, we are trying to find a transfer function, right? And then the following output in response to a step unit input. So we have another information. So the way I like to solve my problems, so I will talk about my approach. So hopefully it will help you to solve your problem. First, find the question. What am I being asked? 2, how much information I can get from the question before solving anything, before doing anything. So what does that step input tell me? Yeah, so it tells me U of t is 1t, that's one thing. So I know in Laplace is 1 over s, right? Part of the question is the plot. What does this tell me? That I have the basic form. I know the basic form of my transfer function. So I call this information number 1, right? So info number 1. Info number 2 comes from this plot, and also my previous knowledge of this is gonna look like this. I can't write it in basic form, right? It's just like, well, I'll call it the proper form. So from this now, what are other information that I can get from my question? I haven't solved anything yet, right? I'm just collecting information. What's the other information I can get from that plot? Your FVT or DC gain is 2, right? So I know K is 2. So number 3, so this is just informations. K is 2. Great. One little thing, if you're here, please pay attention. This is really important. You'll see why. This is a first order system. I know because here I have a slope is 1 over tau. Okay. There are other systems that they will have similar response, but they are actually not, because you have to look at the beginning and they will have a slope of 0. So here slope is 1 over tau. I know this is a first order system, so I can use G over 1, K over S tau plus 1. Now, what other information? So now we have all the information. Now we need to use some thing from before, like from what we learned, some of our skills. I have K, all I have to find is tau. Now, how to find tau? This is the part that you solve the problem. How do you find tau? So the solution starts from here. Find tau. How do we do that? Do we have information from before?
You can multiply 0.66 times.
Yes. So you know y of tau for first order system has to be 0.632 K, right? We know that. I have K. So this is 0.632 times 2. So this is 1.26. Now I have this value and I have a graph that represents the response. So this part, if it was exam, I will give you grid so you can easily read it. But let's say, let's go to the graph. From graph, this is y-axis, right? Y of t. So I'm gonna find 1.26. So somewhere, let's say here, approximately. I'm gonna say from graph, tau approximately is 1 second. So it could be, if it was a graph, could be anything around 1. It's fine. I'm not gonna kill you if you're wrong, like 1.1. So I can say that is from inspection, by inspection. You can even write that and make sure that you explain how did you get that number. Now I can solve. I'm done. 2 over s plus 1. That was a transfer function. So we did both ways. From transfer function to response, from response to transfer function. So these are two types of questions that I might ask you in exam or in a homework with regard to first order system. The third type is in your class participation. So I'm gonna give you time to do your class participation. I'm gonna stop the recording. You have to submit this in class. I'm gonna give you 5 to 6 minutes. Brett has some stuff to do along the way. So he's gonna use that 5, 6 minutes.
Yeah, so as you guys know, we have an exam in a couple weeks, and when we take an exam, on the first page, you'll write your name and then sign that. So just for verification that that signature that you'll put on your exam is the same as, the one that you'll give. I'm gonna come around and give you this little piece of paper, just sign it, you don't have a pen, or you go online, and then just make sure you give it back.
I have some extra. So what you write is your first name, last name, your signature. All right? Yeah, and extra pen, if someone doesn't have, raise your hand, you can grab it. Huh? Class participation is in the module. First order system, CP12. So when you go to CP12, here you see that I asked for show your work to get full credit and submit PDF. Part A, calculate this. Part B, include the passcode. That's the one I told you. Just write it down. All right. Oh, I need to share. Okay, if you're in, watching the recording, go to Carmen module CP12. If you're on Zoom, if you're not, then you cannot complete this because it closes at 4. So just work with Brad and sign that when he's with you. Otherwise, work on your class list. So find out what is the question, what information you have, then answer. All right, don't jump the gun. Yeah, is your question? No. I'm not that confused. Right? Or I might be, who knows? Cannot predict me.
Make sure it's matched with the first contract.
So nominally, some, like when we are dealing with systems, we usually have nominal values. It means that when you design, it was supposed to be 3, for example. But if it's electrical system, due to some losses, you might find 2.98 seconds. So that's actual value, right? Okay, and that's just an information. If you hear like nominal value, it just means that it was designed to be that number. But actual system might have some losses that you don't get your nominal. It doesn't help you solve.
Does everyone have a piece of paper?
Who doesn't have it? Read the question.
Anyone else?
If you're done, raise your hand so I can go through. We have talked about everything. You should be able to do this. Done? Okay. Can't look at that. But we will talk about it. How 3 seconds is for that transfer function. That was the most help I could give you. If you don't have to solve it, don't show it. Don't show it. Huh? How? And read the question though. You done? No, this is. The negative feedback loop. There, hint number 2. If it's not there, if it's don't, you don't say, always you have to help it. The input. The unity feedback is not equal. Unity feedback is. Have you seen that?
Yeah, just write your name and
That's what right. That's what the question is, right? You should be able, so this is a good example. I chose this on purpose because we are moving from doing one task to actual systems, how they are, and apply your knowledge. So this question was chosen on purpose, and I'm hoping that we can like save this moment. Don't forget to give him the paper. You sign, otherwise your exam is compromised.
Did everyone give me their paper?
So put two balls on the phone. I'm gonna give you 2 more minutes and then I'm gonna solve it. So you could, if you didn't finish it, you could follow me. Huh? It's just James. Okay, we have more than one James. Write down last name, first name, and your signature.
Everyone good? Good.
All right, so I'm gonna do this and I'll finish today's lecture another day because based on what I saw, probably most of you need help. So Wednesday, I'm gonna start from second order. It's okay if you need help. I need to know, this was good, I know. So I'm gonna add a page here. use the same approach as I did. I'm gonna share this. Read the question, get information from the question, right? The question says the system is a closed loop system. Information number one, closed loop system. It's used to track the sun, okay? Now this global system is comprised of two parts. A unity feedback, number two, we have a unity feedback. Number three, it has a transfer function, GCS, GPS. So if you don't understand what they are, it's fine. You know there's a transfer function, but it's transfer function of your controller and your plant together is, what are these numbers? I don't have it here. And then where tau is 3 seconds, right? Three information. What's question number one? A. Find time constant for closed loop system. So we need to find what is closed loop system. We have three information before that. Closed loop system has a unity feedback and a transfer function. A transfer function and a unity feedback. If you remember, if you don't have any block and the feedback is a unity feedback, right now it's solved. I know everybody can do from here. So, and if you don't, if it's not said, it's always a negative feedback, but I also mentioned it. From here, then everybody knows what to do. Find the closed loop transfer function and then put it in the basic form, and whatever is the behind S is going to be time constant. We also know tau is 3. So I actually know this is, so T of S is 100 over 3S plus 1, 1 plus 100, 3S plus 1. So it's 3S plus 1 plus 100 over 3S plus 1. I always write them because I always make mistake, cancel out. So TS is 100, 3S plus 101. Now, is this in basic form that I can tell what's the time constant? No. I have to put it in a basic form. TS is divide by 101, right? Because that number has to be 1, 3, 101 S plus 1. Now this is basic form. And I know this is my time constant. I can also call it like tau 1, whatever. Time constant. So it is really important to read the question, find what information you have and what you're being asked for. If you don't know what you're being asked for, you can sit here for 10 minutes and do nothing. So this was the teaching moment. Hopefully it is more clear. You could have done all of this. You should have done just the critical part, critical thinking part. So knowledge base, all of you are good. This is what you want to practice for your exam. Good. All right. Submit if you can write this as submission. So I'm just going to grade based on completion. And I'll see you on Wednesday. You're done with them? Okay. I'll see you on Wednesday.